Good morning or afternoon, everybody. Welcome to Lab 5. This is a lab where we're going to be characterizing the DC and the amplification capabilities of a MOSFET. The MOSFET we're going to be using today is called the BS170. And it comes in a 3-terminal package. The 4th terminal, the substrate, is hardwired to the source, so you don't have to worry about wiring it, the 4th terminal. So what we're going to do, just like we did with the JFET lab, we're going to start with a DC characteristic, collecting a family of curves. And then in the second part, we're going to build it into a basic amplifier and watch it amplify the signal. So for the DC amplifier section, we're going to step up a little bit and use, instead of a DC power supply for VGS, we're going to draw VGS off of a voltage divider. So that is the purpose of these two resistors, R1 and R2. R1 is a fixed resistor at 100K. R2 is a variable resistor at 100K also. So the internal layout of a variable resistor, in this case, is called the potentiometer. And you will be seeing those a lot. We call them pots for short. When you say you're smoking a pot for this, it's a little different than what you're hearing in outside context. And these pots do smoke if you mistreat them. So the potentiometer is set up with a knob that you can twist almost a full revolution, and there are 3 terminals. The outer 2 terminals have a fixed resistance between them of the value that's written on the pot, and in this case, the pot has 100K written right on the back of it. And it comes off of 3 wires. The outer 2 wires have 100K of resistance between them. These are not terribly accurate. It's typically a 20% tolerance, so it could be anywhere from 80 to 120K, but that's all right. This is a forgiving circuit. And then the center lead is called the wiper. And so as you turn the knob, the wiper goes around from one end through the middle, then to the other end. So a good practice that I'd like you to do for the rest of your life is to always center a pot before you plug it into your circuit, turn the knob all the way one way, all the way the other way, and then back and just leave it in the middle. Because if the knob is all the way to the end, these 2 nodes are shorted out, and that shorting out can be damaging to the rest of your circuit as well as the pot itself. Okay, so we're going to use the potentiometer as a variable voltage source using this voltage divider. So if this is a 100K and this is a 100K, as we move the wiper, this is going to go from 0 to half of our supply voltage. So in this case, we're running off of 12 volts. We're going to be able to vary the gate voltage here when the pot's all the way down to 0. And when the pot is all the way up, it's going to be up to 6 volts. Those are a range of gate voltages we're going to use. Okay. We're going to have a drain resistor again here of 1K. And we're going to have voltages measured on the drain. We'll have a voltmeter here for VDS. We're going to use an ammeter for IDS, and then we're also going to be setting the gate voltages to collect our family of curves. We're going to start at 0, 1, 2, 3, 4, 5, and 6. And so from the rest of this is just going to be pretty tedious. We're going to only need one side of our power supply now. We'll just use V1 for giving us our VDD. We don't even need V2 because we're deriving the other voltage from the resistor right here from the voltage divider. So in the first part of the experiment, we're just going to collect a family of curves. We're going to go up to 12 volts, and that'll give us a current of up to about 12 milliamps as well, which is safely under the limits for this transistor. This transistor has a maximum current of I think 300 milliamps, and so we'll be staying safely under its current limits. So with that, we'll just get started. We'll put the circuit together and just start doing our family of curves. All right, so part 1 of the MOSFETs lab, we have our Keysight 33500 Series B waveform generator, ID number 793. We have our Keithley 2000 multimeter, number 383. We have our Agilent EE310A dual DC power supply, number 688. We have 2 Fluke 189 multimeters, number 457 and 464. And we have our Tektronix 2012 mixed signal oscilloscope, number, it's on top, 635. So that is our equipment today. We're using a standard breadboard, the same one as last time. It's labeled 05. Pretty much any breadboard will work for this. So we're going to start by building our circuit. We have our transistor and it goes DGS, drain gate source. And I'm just going to plug it in the field down here someplace in the middle with the 3 leads spread out. And we just have a short jumper here that we're going to use to connect the source to ground. So that goes from the right-hand terminal down to the ground bus, which is already pre-wired to the very lowest strip on the power supply. And then we're going to need our 1K drain resistor. 1K is brown, black, red. So we're going to grab one of those. And that goes from the drain. The drain is the leftmost terminal. Okay, that's going to go up to here to the positive bus. Like so, and we're going to connect our positive voltage to the positive bus. All right, and then we're going to connect our voltmeter from drain to source. So we're going to set up 1 voltmeter over here. We can put it for now in front of the oscilloscope because we're not using the oscilloscope till part 2. Setting our voltmeter on DC volts and our leads. We can take the negative lead and tie it to ground. And let's tie it to ground over here to keep it out of the way. Okay. And then we already have a jumper from negative to ground. So we're going to be using V1 as our VDD. And we'll just need a jumper from there to the board. And then the positive one, we're going to run first through the ammeter and then to the board. So on the diagram, I've got the ammeter here right above the drain, but we're going to actually put the ammeter above there on top of the 1K resistor. So we're going to come out of our positive supply. The ammeter input to the board is the white terminal. We're going to select DC current, DCI. Okay, and then we're going to come out of the board, out of the ammeter to the plus side, which goes to the drain. And then we need another black cable to get from the negative to there. And we have our voltmeter will be connected to the drain. Okay, so we're going to use the red terminal of the voltmeter and we're going to plug it into the right-hand terminal there and then alligator clip. Now I don't like to connect these directly onto the signals, the components plugged into the board, because if you yank on them, you'll unplug a component and your circuit won't work. So what I do instead is I take a jumper wire and connect this to the jumper wire. That way, if you yank on this, all it does is unplug the jumper, but it won't disconnect your circuit. So now we have the drain end connected, and now we just have to connect up the gate end. So to do that, we're going to get our 100K resistor, which is brown, black, yellow. Thank you, sir. We have our 100K resistor that is going from VDD, from the positive bus, to the gate. And I'm going to run that down here. And then I think I left the potentiometer on the front table there. Okay. And then we're going to connect our potentiometer one end to the 100K resistor, the other end to ground, and the wiper going to the gate, which is the terminal in the middle. Okay. Now there's one final little catch to it, and that's that right now the ammeter is going to be measuring the transistor current plus the current coming down through this resistor here. And so What that means is we can either rewire the circuit to have separate currents, or what we can do is every IDS that we can deduct 12 volts divided by 200K, which is 60 microamps of current from each reading. And what we'll find is 60 microamps of current is really inconsequential. So we're now at the point where we can start taking measurements. The pot is centered, okay? And I think we can go ahead and turn everything on. So this is VDS, IDS, and then to get VGS, let us recruit our other voltmeter. Okay, we need a black wire connecting up our ground. We can connect that there. And then the second voltmeter, which is going to give us VGS, we can connect from the gate to ground. So again, we can use a banana plug on the negative side and just connect that to a convenient ground point. We happen to have one right here. And then the positive probe again. Oh, get that on camera. The positive probe here is going to connect via alligator clip. Okay, to the gate, and the gate is the center terminal of the transistor, like so. So we can turn this on, set it on DC voltage. Is that showing up well? Got everything?
Oh, we got another dead one.
Oh, got a dead battery. Okay. Luckily, the equipment manager's right here. We're going to swap out that meter for another one. Luckily, these meters take relatively inexpensive batteries. The type we had before took batteries that I think cost $5 a piece. These just run on AA's, right?
Yep.
Yep. So these, when they go bad, it's not such a big deal. Okay, so we've got VGS, VDS, IDS, and VDD right here. So I think we're ready to go. And before we start taking a lot of data, I would just like to turn the voltage up and see if this even works. So let's set the voltage for, let's say, 5 volts. And it looks like at, here we go, even at 7 volts, we are drawing 1.1 milliamps. So that means the transistor is alive. This looks like a brand new transistor, which is always safer for getting things to work. And so now we can go ahead and set our gate voltage to 0. To get the pot bottomed out, to connect this terminal to this terminal, we turn the knob all the way counterclockwise. So right now we should be having 0 volts on the gate. Let's set up our voltage on the drain at 12. Okay, so what we see that for 0 volts on the gate, we have 12 volts VDS and 12 volts VDD, which means there's no current flowing. So that's also a good sign, it means our transistor's shutting off. So what we're going to do now is we're just going to take our VGS equals 0 curve. We're taking our first curve. So let's bring the voltage down to 0. Okay. So with a VGS of 0, here's our VDS now of 1. And IDS is 0. VDS of 2. IDS is 0. VDS of 3. IDS is still 0. It's 16 microamps, but that's going to be 0 on a milliamp scale. VDS of 4. 20 microamps, again, very little. VDS of 5, 26 microamps, still basically nothing. VDS of 6, 31 microamps, again, very small. VDS of 7, 37 microamps. It's still not really passing any current. VDS of 8, 42 microamps. VDS of 9, 47 microamps. VDS of 10, 52 microamps. VDS of 11, 57 microamps. VDS of 12, 63 microamps. At this point, we're just going to pose a question, how much current is going down through R1 and R2? So when you have 12 volts divided by 200K, that's 60 microamps, and sure enough, we're getting about 60 microamps here. So what it's saying is that all the current coming down through here is actually going through R1 and R2. None of it's going through the transistor. Okay, and so that's something you can adjust in your curve. If you'd like to deduct VDD divided by 200K from your IDS measurements, your curves will be a little bit more accurate. We're going to make, because I don't want to be dealing with changing VDD, giving a change in VGS, we're going to recruit a second power supply just to give it plus 12 at the top. And luckily this circuit has two buses, two power buses, and we're going to just use both of them. So we're going to set, to take our next curve, we're going to set V1 at a constant 12 volts. And then we'll use V2 to measure VDS. So V1 is going to be a constant 12 volts. Okay. And we're going to, okay. We're going to reconfigure the jumpers here so that both outputs are positive. So V1 is going to be a constant 12 volts. Instead of running it to the ammeter, we're going to run it to the board, to the upper power bus. Okay, constant 12. And now V2 is what we're going to be using to vary our supply voltage. All right, so we're coming out of there into the ammeter, out of the ammeter into this bus, which goes to the drain. So the upper bus is the gate, the lower bus is the drain. All right, so let's see what we got now. We've got still 1 volt on the gate, that's good. And now we can start our VGS of 1 curve. So right now we have a VDS of 0 and an IDS of 0. Okay. And then we're going to go for VDS of 1. And IDS is still 0. Now this current is not going through R1 and R2, so this is a direct measurement of IDS. So VDS of 1 and 0, 2, 0, 3, nothing. Let's just cut to the chase and go to 12 and see what we get. Nothing. So the VGS of 1 curve is still flat. The transistor is still in cutoff. So that curve was quick. Let's go to a VGS now of 2. So we're turning VDD all the way down. We're going to bring the pot up to 2 volts. Okay. Oops. Oh, we just have to wake it up. Okay. So now let's go ahead and do our 2 volt curve. We have a VDS of 0 and an IDS of 0, 4.6 microamps. That's 0 just between us. There's 1, 20 microamps. There's 2, 20 microamps. There's 3, 21 microamps. 4, 22 microamps. 5, 23 microamps. 6, 23 microamps. 7, 24 microamps. 8, 24 microamps. 9, 25 microamps. 10, 26 microamps. 11, 27 microamps. And 12, again, 27 microamps. So again, the transistor, even with 2 volts on the gate, is not really turning on. So now let's go to 3 volt curve. We're going to go up to 6 volts. So 3 volts, we're going to turn the potentiometer till that reads 3. So we now have 3 volts on the gate, and let's see what we see on the drain. So at 0 volts, 12 microamps. Whoa, very different. I'm cranking the voltage way up, and we're still not getting to 1 volt on the...
No, in other words, the transistor's on.
It's on, and it's really... We're getting up to 10 milliamps. I really don't want to go much above that. And we still have a VDS of close to 0. So the transistor is on and it's very conductive. So let's go up to 12 volts. And we're getting 12 volts, 12 milliamps, but a VDS is still close to 0. So what that means is that somewhere between 2 volts and 3 volts, we went from off to fully on. So instead of continuing on to higher voltages, let's take some voltages between 2 and 3 and see if we can fill in those curves. So we'll turn this down, but just to keep in mind, VDS stayed at 0, which means the curve is almost vertical. The transistor is on like a short circuit. So let's take some voltages in between. So let's do 2.3, 2.7, let's do 2.2, and 2.4, 2.6, and 2.8. That ought to give us enough details to get a good curve. So there's 2.2. 0 gives you 0. 1 volt VDS is at 0.17 milliamps. The transistor's coming alive now. Two volts is 0.18 milliamps, or 183 microamps. 3 volts is 0.19 milliamps. 4 volts is 0.19 milliamps. 5 volts is 0.20 milliamps. We can see we're getting into constant current region now. 6 volts is 0.20 milliamps. 7 volts is 0.21 milliamps. 8 volts is 0.21 milliamps. 9 volts is 0.22 milliamps. 10 volts is 0.22 milliamps. 11 volts is 0.23 milliamps. And 12 volts is 0.23 milliamps. So the transistor's on, it's showing good constant current behavior. So let's do a 2.4 curve, and a 2.6 and a 2.8, and then we'll be done. So now let's go to 2.4. Okay, this is a 2.4 volt curve, and we have VDS of 0 and IDS of 12 microamps. A VDS of 1, 1.17 milliamps. A VDS of 2, 1.2 milliamps. A VDS of 3, 1.23 milliamps. A VDS, oops, I have to wake that up, yeah. A VDS of 4, 1.26 milliamps. A VDS of 5, 1.29 milliamps. A VDS of 6, 1.32 milliamps. A VDS of 7, 1.34 milliamps. A VDS of 8, 1.37 milliamps. A VDS of 9, 1.4 milliamps. VDS of 10, 1.44 milliamps. VDS of 11, 1.48 milliamps, and a VDS of 12, 1.51 milliamps. Okay, that's at a 2.4. So let's do the 2.6 curve. We'll back off VDD again and go to 2.6 volts. It's a little twitchy, it's a little touchy here, but we'll try to get as accurate as I can. 2.6 volts, okay? So VDS of 0, we got 0. Okay, we're cranking it way up. It's going to take us, oh, there we go. It suddenly came up. The VDS of 1, we got 4.7 milliamps. Wow, okay. A VDS of 2, we got 4.8 milliamps. The VDS of 3, 4.9 milliamps. The VDS of 4, 5.06 milliamps. The VDS of 5, 5.20 milliamps. VDS of 6, 5.35 milliamps. VDS of 7. Remember, we're stopping at 12 milliamps. If we hit 12 milliamps, we stop. VDS of 7, 5.5 milliamps. VDS of 8, 5.64 milliamps. VDS of 9, 5.81 milliamps. VDS of 10, 5.99 milliamps. VDS of 11, 6.19, 6.20 milliamps. VDS of 12, 6.4 milliamps. So that's our 2.6 volt curve. Let's do one more at 2.8, and I've got a feeling we're not going to get a complete curve at 2.8. One thing people are remarking on is sometimes they see a little bit of variation in these current if you let the circuit sit for a while, especially at higher levels of current, that they notice the current starts to drift a little bit. And that's because the transistor is probably thermal drifting. It's warming up a little bit because of the extra current. And as it heats up, its characteristics change, including its current. So here's our 2.8 volts VGS. We're going to do our last curve. 0 gives you 0. Okay, I'm cranking this up, try to get to 1 milliamp. We're not even close yet. Sorry, to 1 volt. Yep, so 0.3 volts. Let's just see if we can get it to 1 milliamp. I don't think we will. Oh, there we go. So it's cheating a little bit, but we get to 1 volt at 13.5 milliamps. So that's about all we're going to get from that curve, is just that very first point, and then it's going to go off the scale. Remember, we're cutting off at 12 milliamps. So what we've seen, this transistor is very, very twitchy. A very small change in VGS gives us a large change in IDS. And this is a high gain transistor. So with that, we should have enough data to get a good family of curves, and we will go ahead with the lab and build our little amplifier.